Okay, in this lesson, we're going to talk about normally distributed data, which follows the bell shape, and we're going to look at the 68, 95, and 99.7 rule. So when we have these questions, they are always going to tell you that the data is normally distributed. And we know when it's normally distributed, what it means is if you put the data into a graph, so even if it was a histogram, we see this perfect bell shape. Okay, so and then what we see is it like that. So a normal distribution means that it's the symmetric shape. So if you put a mirror down there, both sides look the same. Okay, so this is normally distributed. So when we have this data normally distributed, we often talk about the center, but we refer to the mean in this data. So if we remember back, we can use the mean if the data is symmetric. So we're going to use the mean, and we're also going to talk about how the data spreads around the middle. So when you have your mean in the middle, because it's symmetric, that means we would see 50% of the data occurs before the mean and 50% of the data occurs after the mean value. Okay, so this is when it's symmetric. Alright, so that's what we first need to remember for that one. Okay, continuing on with this normally distributed data. So remembering this rule will only be used when we talk about and they say that it's normally distributed data. Okay, so which means it's the bell shape. And when we have this bell shape or normally distributed data, we can use the standard deviation to say how much the data falls around the mean. So if you look before, I'm just going to draw a separate one. So if we think about it, we had the mean in the middle, and we knew that there was, say, 50% above it and 50% below it. Oops. So what we're going to see now is this, if we use the standard deviation, so if we find a value for the standard deviation, and that's sort of found using our calculator. So if we add to the mean one standard deviation value, or if we minus one standard deviation value, what we find is if you collected 100 people's, if we collected data of 100 people and we said the mean was there and it was normally distributed, what you're going to see is that 68%, or if you had 100 people, 68 people would lie between this value, which is the mean minus one standard deviation, and the mean plus one standard deviation. So it helps us to see how the data spreads out in different examples. So when you have one standard deviation, you have 68% in the middle. So then what you have to realize is that obviously if you had your whole data set, you'd have 100%. So if we're saying 68 is taken up in between these two values, what we often need to refer to is these pockets. So if you do 100 minus 68, you have 32 left. So make these little pockets 16%. So 16%. So what we're saying, if you have normal distributed data and you go up to this value of the mean plus one standard deviation, if you were sitting on a value, it means only 16% of the data is bigger than that value. Okay, or you could go the other way, the mean minus one standard deviation, there's 16% of the data is less than that. And we'll see how that plays around. So this is always the case when the data is normally distributed, the bell shape. So that's what happens when you have one standard deviation. So let's have a look. I drew these diagrams. So we might want to pop in here. So that was in the mean, and we had one standard deviation above, and we had minus one standard deviation below. Okay, so there's that. So obviously here, if you go two standard deviations, so if you see we have the mean, then you have 1, and then you add another standard deviation, or you minus 2 standard deviations, what you see is 95% of the data lies in between. So you can see here, between here and here, there's 95% is lying in between. And then we've got 5% left over, so those little pockets become 2.5%. And then the last one that we will talk about, because in this last one, we're nearly covering the whole bit of the data. Because if you go up 1, 2, 3 standard deviations, so up there, and if you minus 1, 2, minus 3 standard deviations, you can see in between those plus and minus 3 standard deviations, we have 99.7% of the data. So that's nearly the whole data set if you think it's very close to 100. So these pockets are very tiny when you have that, but they are still there. So there's those little pockets there, and there's 0.15%. So just be careful that when we say them, that's 0.15%. So if you changed that to a decimal, that would be 0.0015. Okay, so be careful because that's actually 0.15 over 100. All right, so just be careful because you'll see when we're calculating to make sure you convert that percentage to that. Okay, so here, this diagram, it's just showing you how you can break them all up into little individual percentages. So you could see here, when I said you were minus 1 standard deviation or plus 1 standard deviation, we had 68%. So you can see they've just split it in half with that mirror image. So they're saying that this little pocket between the mean and minus 1 standard deviation is 34, and so you can get the same. And then you can see here when we had plus or minus 2 standard deviations, we had, remember if you thought about that, remember in there we had 95%. So it shows you how you break it up. If this little section here is 34, then it makes this bit in here 13.5. So this is just sort of breaking it up into little sections, and I'll show you how we can use that if you want to work out some of the questions. Okay, so here we're going to go with doing this question, and it says the distribution of delivery times for pizzas made by House of Pizza is approximately normal. That's our indication that this is normally distributed. So we've got that bell shape, and we can be using the 68, 95, 99 rule. Okay. Now, you'll see too when you're going through the questions, once they've said that, they generally will state the mean. And here we've got the mean is mean waiting, delivery time is 25, and then they'll give you the standard deviation. So what they gave us there is that mean value and the standard deviation, which I've been writing as SX. Okay. So here it says in the question A, what percentage of the pizzas have a delivery time of between 15 and 35? So with these questions, I often find it's better, you just, as soon as you see it's approximately normally distributed, just draw your bell shape, like just quickly sketch it up, and then it'll help you easier to visualize or understand. Because what they're telling me is they're saying that the mean is 25 minutes. Okay, so and they've told me the standard deviation. So if I added 1 standard deviation, that means the number would be 25 plus 5. So that makes that 30. So just to be sure how I got that number, that was the mean plus a standard deviation, which was 25 plus 5, which is how I got 30. So there's 1 standard deviation. If I went up another one, so I'd add another 5, that'd be 35. And, if I add another one, I'd be at 40. Now, you can go the other way. So if I minus 1 standard deviation, I'd be at 20 because I'd minus 5. And if I minus 2, I'd be at 15. And if I minus 3, I would be at the value of 10. Okay, so you'll see that most of your questions are always going to be connected with these numbers of plus or minus 1, 2, or 3 standard deviations. So in this question A, when we look at it, they're asking us what's the percentage between 15 and 35. So if you look at 15, here's 15 and here's 35. And you can see that is lying between the plus and minus 2 standard deviations. So we knew when it was plus or minus 2 standard deviations that 95% is between those two. So the answer for this one, for A, what percentage of pizzas have a delivery time between 15 and 35? We'd say 95%. Okay, if we look at B, it's saying again, what percentage of the delivery times is greater than 30? So if you look, 30 is at our 1 standard deviation. So I'm just going to draw that here. So when we looked at when we were 1 standard deviation, so remember we had the mean, if we went 1 standard deviation minus 1. So we said in here was 68%. But we said that this little pocket, remember, we said the pocket was 16% because we had 32 left over. So when we say when it's 30, how much is greater? Well, greater will be this way. So when it says how much has a delivery time greater than 30 minutes, we'd say there's 16% that's greater. So that's the answer to B. Now, in 1 month time, the House of Pizza delivers 2,000 pizzas. So that's what like they've surveyed and they've done 2,000 cases. Approximately how many of these pizzas have a delivery time less than 10 minutes? So if you look at 10 minutes, we go to our little diagram here. 10 is minus 3 and they're saying less than 10. So that's that way. So if we thought about when we had our bell shape and we had minus 3 standard deviations and plus 3 standard deviations. If you go back and look, remember this little pocket here, because that's what we want, the less than 10, was that tiny 0.15%. So what we want to say when we said, well, we know of those we want 0.15% of that 2,000 people or pizzas, delivered. So we want to work that out. So you can either change the percentage to a decimal or make it a fraction. So if you look before, and we can do the percentage. So I'm going to say we've got 0.15% out of 100 times 2,000, and then we get equals 3. So approximately how many pizzas were delivered in less than 10 minutes? There was 3 of them. And if you have a little bit of logic, it should be a small amount, and less than 10 minutes, that's pretty quick, so there wouldn't be a great deal. So think logically too, in case you stuff it up. If you had 30, try to think, well, that's a bit unreasonable. I doubt that's going to happen, and that can help you trigger an error. Okay. Lizards in a reptile house are given cricket nymphs to eat at feeding time. The lengths of the cricket nymphs are approximately normally distributed. So as soon as you see that, you know you're doing this bell shape and you'll be using the 68-95 rule. And once again, so they'll tell you the mean and they'll just tell you the standard deviation is 2.3. So when we're thinking about our little diagram, that's the mean and that's what we're adding and plussing. And it says use this rule to determine the percentage of crickets that are expected to be longer than 15 millimeters. So what you should do is I suggest you just quickly draw up, as I said, just quickly draw up your normal bell, chuck the mean in the middle so you know that 12.7 is the mean. Now the number they want is more than the mean, so we'll keep on adding a standard deviation. So if I add 1 standard deviation, means I add 12.7 plus 2.3, and that would give 15. Okay, so when we did this 12.7 plus 2.3, that's 15. So that's what they're talking about. So they essentially, the question's asking what percentage is more than that 15? So we need to know what this percentage of this pocket is. Now, because it's one standard deviation plus, we know those little pockets are 16%. So we'd say 16% are bigger than the 15 millimeters. Okay, in the next one, so what the percentage of crickets expected to have a length between 8.1 and 15. So I was telling you all the time, these numbers will relate to adding or subtracting the standard deviation to the mean. So we already saw, so we know the mean is at 12.7. We know if we go up one standard deviation, we got 15. Now, if we minus one standard deviation, we would get to 10.4. And then if we minus another standard deviation, we'll get to 8.1. Okay, so this is what they're asking us to find. So what we have to do is remember back to those little pictures. When we were minus 2, look at these. This little pocket was actually 2.5%. But when we were up at only one standard deviation, like we saw before, we knew this little pocket was 16%. So what the question is asking is how much percent lies between there and there. That's the question. So there's a couple of ways. So we could just simply go, all right, if we had all of it, and we're going to minus those two little pockets, the 2.5 plus the 16, okay? And then we'll end up with 81.5%. So we could do it this way, and that's probably the quickest way. So we'll stick with that. The number of cricket, I'm up to 3. Number of cricket nymphs expected to be shorter than 10.4 in the sample of 150. So I can see up there, and I'll just redraw it again, that I saw if I had my bell shape, the mean was at 12.7, but if I went down one standard deviation, I was at 10.4. So they want the number that is shorter than that. So that would be all the ones going back this way. So what do I know about that? I know when I have one standard deviation that this pocket is 16%. So I want 16% of the sample of the 850 are less than that 10.4. So we can change that to a decimal. So I'm just going to go straight to that. It'll be 1.6 times 850, which equals 136. So 136 are less than 10.4. Okay, a number of matches contained in boxes of light rights are normally distributed. So they've told me it's normally distributed, they give me the mean, and they give me the standard deviation. If a box is rejected if it has less than 46 matches. So in this whole sample of 640, the number of that boxes that would be rejected. As soon as we know that we've seen this, it means they're using the 68-95 rule. So let's draw it up here. So if I just draw my bell shape, I know I've got 50, and somehow they're talking about 46. So I can see I'll need to go minus standard deviation. So if I go minus 1 standard deviation, that would take me to 48. If I go minus 2 standard deviations, that would take me to 46. So they said if they have less than 46, they're rejected. So anything less than that is rejected. So I'm at 2 standard deviations. So when I see that, I know at 2 standard deviations, that little pocket is 2.5%. So 2.5% of our sample, or the group of boxes we've got, is going to be less than that. So we're going to go 2.5 of the 640. Okay, so then we can change that to a decimal and times it by 640, and we end up with 16. So this was a multi-choice, so there I would circle C. Okay, and now it says the number of matches contained in boxes of Light-Rights are normally distributed. So this was a new question. So once again, they're telling me that the mean is still 50 and standard deviation is still 2. And they want to know what percentage lie between 48 and 54. So when we do our bell, if we're writing them all out, that 48 and 54 are going to appear when we add or subtract the standard deviation. So the mean was 50. Now, if I go up 1 standard deviation, I'd be at 52. If I go up 2 standard deviations, I'd be at 54. So that's what they're talking about there. And I need to go to 48. So if I minus 1 standard deviation, I'm at 48. So the percentages that lay between those. So the question is pretty much asking between here and here. So what we're going to say is you could do the pocket thing again. You know, when we have 1 standard deviation, that this pocket is 16%. And when you have when you're up at 2 standard deviations, this pocket is 2.5. So if you're trying to find out what's in between here, we could do what we did before, where we said 100% minus those 2 pockets, which was 16 plus 2.5, and it gives the same, 81.5%. Okay, we could do it this way, or I'm just going to show you how we could use the other diagram. So bear with me. So what I'm saying is you could use this diagram as well. So here was at the minus 1 standard deviation, and here you're up at the 2 standard deviations. So what you could do, you are here and you're going up to there. So you can add all those percentages up. So if you do 34 plus 34 plus 13.5, that will also equal 81.5%. So that's another way you can do it if you like. Okay, the length in centimetres of a sample of 16,000 trout were approximately normally distributed. So I know I can use a rule, and here they go, mean and standard deviation of 1.7. The trout with a length less than 2.2 are undersized. The number of undersized trout in the sample. So just quickly drawing it up, I'm going to find out where that 2.2 lies in terms of the mean and standard deviation. So we've got 25.6, and then I've got, I want to get to 22, so I'm probably going to go minus 1 standard deviation. So I'm going to say 25.6 minus 1.7 is 23.9. And then we've got minus another we're not quite at it. So if I minus another standard deviation of 2, I get to 1.7. I get to 22.2. So that's the number that we want. And it says the number of sites in the if it's less than that, it's undersized. So we want to go this way. And remember, when we have 2 minus 2, that little pocket is 2.5%. So we're going to say, all right, 2.5% of this sample of 1,600 are undersized. So I'll change that to a decimal and times it by 1,600, and we get 40. If you want to change the percentage, you can always do it like this as well. Just make the percentage over 100 and times 1,600. That's the same thing. Okay, on your calc, that's fine. So we end up with 40. Okay, so we're just going to do the start of exercise 1H, and I just want you to do questions 1 to 5 for now.